So at this point, I was thinking that to do a explicit problem where you can actually calculate the total entropy and see the functional form of this particular system. So we'll focus on a very, very particular problem, and then we'll see that how these fluctuation theorems that just proven by Abhishek and also today, yesterday. So how they can be validated, okay, in a pedagogical problem, but I think with the setup of this optical tweezers and colloidal particle trapped in it, one can also test in the lab, okay, and simultaneously you can do the analytics here, so it may be more relatable. Okay, so the system is particle, colloidal particle, following this dynamics, overdamped dynamics in harmonic track. Okay. So the first problem, there will be no external drive, but the system is prepared in distribution. So initial distribution is non-thermal, okay, and it will relax to a thermal. On the way, how and what is the entropy production, okay, that we will calculate, okay, and then we will see what is the distribution of this entropy production and how these distributions are satisfying the fluctuation theorems. So this is the basic plan of the first, say, 1 hour or so, and then I will go to the generic formalism. Just so there are now so far there are many discussions and proofs and all, but there are some comments I will do in the last half an hour, okay, and then finally we relate the entropy production to some information theoretic measure. Very briefly, that will be elaborated more in some biological system by Edgar, something called active hair bundle. Okay. Anyway, so let's start. So this so we have this equation of motion of the particle gamma s dot, as Abhishek took, just specifying this thing to a particular force field which is harmonic trapped. Now this k is constant, gamma is as usual constant, and with some thermal noise. This standard, this same.
Arnav, can you write a little darker if possible, or bigger? It's hardly visible from here.
Bigger fonts.
Bigger fonts.
Yeah.
And also darker.
Okay. So this eta follows Gaussian this thing. So eta t prime is 2 gamma t. I put kb to be 1, and then delta x minus prime. And as I said, this system is prepared in some non-thermal distribution initially. So for this analytic progress, we say this is the initial distribution. This size is okay? Is it?
Yeah.
Yeah? So this is now root over k, okay, 2 pi sigma square exponential k x naught square by 2 sigma square, where sigma square is not equal to the temperature of the bath. Okay, sigma square can be anything, but it is not temperature. So this is my chosen initial condition, right? So now the system will relax from this to some other, like the equilibrium distribution, but in a time-dependent manner, of course. So this is a transient case, I would say. So for that, so what will be the distribution at any time point? So this we first need to calculate. So there, so from here we can actually, so this is, we first need to write a formal solution. In this case is very simple. It's eta over gamma. Then this is x, so I'll just write it d dt of explicit power gamma d, then x is 1 by gamma. Correct? Then x is x0, that's here, to the power minus kt over gamma plus to the power minus kt over gamma by gamma. So where you have t prime is lesser or equal. Correct? So any question? Just now you see this is a linear function of this. So that means that p of eta, that is the Gaussian. So P of eta is Gaussian. That means it is same as P of x is a linear function of some Gaussian variable. So P of xt has to be Gaussian. That means I just need to calculate the average and the second moment. These are the Apradeep?
No.
So now, so this, what is my x average? X average is x 0 average e to the power minus kt by gamma. So I don't take t tends to infinity limit, it's all transient, so I keep all the terms. Okay. Now this is what, this is 0, right? So this one is 0. What about the next term? Next term is also 0 because when I take the average of this, it goes to 0 again. So essentially, x average is 0 for all time. Then what about x square average? So there, so I have xt, so x square t average is x0 square average to the power minus 2 kt over gamma. Then I have a cross term, x0 eta, but x0 is initial conditions chosen, so they are independent random variables. So x0 eta average is x0 average eta average, which again, so there is no cross term. Then I have this fellow left, so this is e to the power minus 2 kt over gamma by gamma square t. Then you have dt prime, say dt double prime, eta t prime, eta t double prime, e to the power k by gamma t prime plus t double prime. And then I have to use this.
Sorry, order one question. So x0 is anyway random, right? And following that Gaussian.
Yes.
So what was the point in taking sigma square not equal to t? I mean not proportional to t?
Because I want some distribution which is not thermal. Moment I put sigma square to be like t,
Yeah.
like that, then it is thermal. So there is no point in going from, like, there is no relaxation. The system is already
But you're
in
still,
equilibrium.
still taking it Gaussian. So
I have.
without that it will fail, something else.
No. This is a particular example
Okay.
where I can do some analytics.
Fine.
You can take any kind of distribution, the analytics will become
Yeah.
cumbersome. So then this I know, I guess, written. So I just put it here. 2 gamma t delta t minus t prime minus t double prime. So then what happens? Then this x0 square is there, so it is sigma square by k e to the power minus 2kt over gamma. Then I have e to the power minus 2kt over gamma square. Then it is delta function. So 2 gamma t will come outside, and we will left with dt prime e to the power. So t prime is equal to t double prime will only contribute to the integral because of delta function. So we have 2k t prime gamma. Correct? So my gamma, one gamma cancelled. So then I have sigma square k e to the power minus 2kt over gamma plus this I can, so e to the power minus 2kt over gamma by gamma, then gamma over 2k, and then I have to the power 2kt over gamma minus 1. Clean? So what happens here? Then x square t average is the sigma square by k e to the power minus 2kt by gamma. Then I just, so again this gamma cancels. There is some,
shouldn't there be an x?
there is some t there, right?
Half factor.
Wait.
Because the dt double prime integration should be from 0 to t prime. And you have a delta.
So there is a half here.
There is a half factor.
There is a half factor here. So let me. So you are saying this should be.
Yeah.
So this is gamma t, right?
Should be.
This should be gamma t. So this 2 is not there, and what we get is. T over 2k 1 minus e to the power so this is my x square at x square average at any time t. Correct? So my full distribution is no, KB, I mean the KB is 1.
Second one, 1 minus ds2 minus 2 kt by 1.
Oh, right, this, of course. This one, right? So 2 kt by 2. That's good.
You overestimated yourself.
Exactly. Exactly. I thought that I can, but what about then P of xt? Just a second. Yes.
So P of eta, eta itself is a distribution, right?
Yeah. So that is Gaussian. That's why I have as not only that, because x is a linear function of eta. That's why P of xt is also Gaussian. That's why I need to calculate only two moments, not more than that. Because two moments are they are the parameters of Gaussian distribution. First two moments.
Did you say that it is equal to P of eta? I think I missed some line of argument.
This one, P of eta. So P of eta is Gaussian.
Yes.
Then x is a linear function of eta. So P of xt is also Gaussian. That's the line of argument.
Meaning it's not exactly equal, but
No,
it's
not
Gaussian.
equal.
He
So
did
it's
not do
Gaussian.
it.
So it is not equal. I told you, right? So this.
Yeah.
In the equality sign.
Yeah.
No,
No,
the-
it's not.
No, no,
You're
no.
just saying that they have
I mean,
similar
they are
distribution.
similar, same distribution, not similar, same distribution. It's Gaussian also. Okay. But of course, the moments etc. will be different.
Also, since the system is evolving towards equilibrium,
Hmm.
sigma square will change.
Change,
and
yeah.
go towards.
Yeah, that is the time dependence there.
No, sigma square will not right?
Actually,
Two cancels.
This 2 is not there, no?
Two cancels.
To the t by k only will be there. Somehow I get this 2 right.
So there will be two there, two cancels.
No, but then Vijay pointed out is a half should be there.
No, but the two cancels. There is a 2 gamma t and then 2 kt.
2 gamma t and 2
Then
k
divided
t.
by
Exactly. Then this 2 cancels out. And then this, okay. I don't have this. Good. Too many 2s.
Yeah. Exactly.
yeah, no,
So-
just one small comment that you can write Fokker-Planck equation
And solve it, yeah.
and
Exactly.
solve the first moment and the second moment as constant time.
This is so 2 ways to calculate. One is this, you can directly from the solution, or you can from the dynamical, the equation of motion itself, you can multiply x and get a dynamics of sigma. I mean sigma of
But
t.
our aim is to calculate sigma square as a function of time. I mean,
Yeah,
what is our
of course.
final destination?
Final destination is this, to calculate the anytime distribution function. Okay. So then what you have is sorry, let me. So 1 over 5. So this is my P of xt, where x square t is given by this full distribution.
So this is more like a problem that you're starting with a state. The
Hmm.
initial state is also some, you can associate an effective temperature. So
Ah,
you are
that is true.
having some 1 bar at some temperature.
So
and
you
putting
can
that
think of
particle-
this particle is equilibrated in some bath. Then you change the bath or pick the particle.
And put it
It's a kind of quench, if you like in these terms. So that system relaxes to this distribution. Then the point is, first we need to calculate what is my in this process of relaxation. So the next step is this, to calculate the total entropy in this relaxation process. Okay. So the one first aim is there. Now the next step is the total entropy calculation for this particular case. Okay. So for that I need to
So this board is a consider like decorative board with another matter.
I don't have another hand. I have 2 hands. How can I generate another hand?
Put the paper in.
So now, delta S total is a sum of system and path entropies, right? So delta S system plus delta S path. Fine. So we have the initial distribution, we have the distribution of time, and we know how to define system entropy, log of P, right? The fluctuating entropy without taking the average. So that is, the first term is log. So this is where we have reached. Then this is where we have started. And then we have the heat dissipated during this relaxation process. Yeah.
So why are you not using focal point equation to calculate P except T and
You can, this is a parallel process.
but will this get same?
Same. Then this one is, I already know the answer, so this is plus ln P of x0 by of x t. I just a disclaimer, am I too slow, like particularly for the students, or I can be faster? Is it like, okay, I'm doing the every steps. Is it okay?
Yes.
Okay, so I'm as if I'm taking a class. It's not that. So if you feel bored, you just can tell me that no, you can go faster. Then Q by T. So this one from W minus, so all are fluctuating. So this is the first law in stochastic phenomenon that we have Abhishek discussed. So now this thing, we don't have any protocol and there is no non-conservative force. So W has to be 0. So W, so this thing you have, so to get non-zero W, you need the lambda dot, you need non-conservative force. Nothing of such is present here. So W is 0. Okay. Then what is the first term? So this is ln K by pi sigma square. As I have chosen this distribution. Then this distribution I got this is my system entropy. So there was a question that this is why it is called system entropy and all. So so it has through this x square average, you will see the contribution of the temperature, right? Somewhere I have, it's not there anymore. But anyway, x square average is a function of temperature also. Temperature and gamma, they are the bath properties, right? So though it is system entropy, but this also encodes some bath information as well. But why it is called system entropy? Because it is the distribution of the particle which is the system in this particular case, and the rest is bath. So that is why we call it a system entropy. Okay. Then minus this one is T, so this is K over T, then 2 into this, so x square minus x naught. So this is the change of the potential energy, which is the only energy in this case because we are in the overdamped limit. So this is the change of energy. So this is my delta S. I like these boxes. Right? Clear? Now I am just rewriting a bit little easier way.
X0 square minus x.
What?
Shouldn't it be x0 square minus x?
This is minus becomes plus. So
No, that
or no. You are correct. Yes. So this is the final state is x. Initial state is x0. So that is the very good. You are awake.
We are moving the colloidal particle from x0 to x.
We are not moving, it moves.
It is moving.
Yes, it is relaxing. It is relaxing towards. So it is like experimentally that you have chosen, there is a particle which is already in equilibrium in some path, say T1. You picked up and throw it immediately in some other path, which is T2. Now it is relaxing. Okay?
But it's in the same, there is no harmonic trap.
No, there is a trap, but constant trap.
The P is constant.
Constant. The K is
So you are just lowering the temperature of
I just lowered it. It's a quench, kind of. Okay. So now you see how the particle relaxes to the new path,
Sorry.
and on the way of.
And one question. So, in principle, you could be heating. Okay, you say that you are quenching the temperature, but it could be that you start with a very narrow distribution that expands, or a very wide distribution that collapses later.
Yeah.
Because the x squared initial is arbitrary for you, no? It could be either smaller than the equilibrium
Yes.
square,
So
or bigger.
so basically, x square depends on two things. One is k, one is t. Right. So if you so you can change your x square average by changing either t, that's I'm doing here, or changing k, that you are proposing. So both ways it is possible, right?
No,
So you,
actually, my question is not about changing t or changing kappa. It's about the initial value of x squared. That talking an experimentalist thinks about doing.
right. Maybe it is easier for
them. They can control.
the k is a more controllable parameter than.
Sure, but they could imagine of starting with a highly confined state where x square average is
Then
small,
check
and then you will relax the equilibrium by
yes,
doing like this, expanding.
Yes.
Or they could think about the other process. They start with a very
And
broad, and
then
then it will collapse with
Yeah, both
converse
ways.
equilibrium.
both
state.
yes.
So both are in your
Both are there. Both are there. Yeah.
So x square average initial is
X square more it will be general if I talk about the x square in the language of x square average. I have some x square average in the beginning and some in the end. In the meantime, it relaxes.
Okay.
And how do we ensure that it's always greater than or equal? How are you coming to that?
I'm coming to that. So it will emerge. So now if I just rewriting, skipping a bit of algebra, 2-3 steps, nothing else. So I will define this, what is alpha? X square plus half of. So I reserve beta for something else. So it is not 1 by kbt or something, okay? This is maybe a little bit, so this is not 1 by t. This convention is there, please. So then I have kappa. So what are they? So alpha is k by 2 sigmas. But this is all about rearranging, so nothing new. T sigma square. Then beta is T minus K. So this I am collecting all the non-random quantities. So these are all averaged, so they are non-random.
So you all know one question. So in the internal energy, that kinetic energy difference is also now non-zero, right? Because your starting kind of kVt half mv square was equal to kVt of the initial x0. And now you have a different xt. So shouldn't that be
so
taken care of?
actually, so what you are saying is this overdamped framework may not work in case of quench. That's what you are
No,
saying.
I'm just saying that in the delta U, shouldn't you include that difference?
Kinetic energy difference.
Initial state minus final state.
Here within the framework of overdamped, because underlying dynamics is overdamped, so we don't have velocity there. So that means that at any time point, the velocity is equilibrated.
2 kVt, right? Half
2
mv
kVt.
square average is kVt, even with this dynamics, right?
But there is no velocity here.
No, but
No.
there's no velocity, but still at any given point, this system still will have the half mv square average is equal to kVt, right?
Right.
I mean,
So,
from
but
the
here it is, what he is saying is there is a kind of quench thing, right? So it was, so if you think of sigma as a temperature, some other temperature, then the half mv square average is there is kVt, correct? That T, not the final T. Now it is relaxing towards that, right? That's what you're, now it's relaxing towards, but I'm not including that one here, but it is maybe important. I haven't thought of, frankly speaking, with this thing. But in the quench thing, so that's why I was kind of reluctant to use this sigma as other temperature, other bath. But I think it is, if you do it more carefully, you have to include this difference, maybe, but I haven't done it. Okay, but it's a good point that you have raised.
But that will be a constant term because T is downstairs. Right?
That is anyway, if you take the average, then it will add another constant to this entropy production. That may happen,
but
that
temperature is changing with
matter,
time, right?
Huh?
Your effective temperature is changing with time, isn't it?
If you define the effective temperature, of course, but here the expression that we had, x square average, that they are all the temperature of the bath. So there is no effective temperature so far. If you define effective temperature in that way, then it may. But I am not defining any effective temperature so far. The temperature that is there in the x square average is a real temperature. Real temperature of the bath in which the particle is.
Okay, so you're saying the half mv square will require the bath temperature,
Bath
not the sigma of the x.
No,
Yeah,
it's
okay.
a bath
So
temperature.
in that is not changing.
No, that is not.
That is noise.
That is not.
Okay. Sorry.
Sir, is the equipartition still valid for an overdamped case? Like suppose we take velocity as root 2 k Boltzmann d by gamma into beta d, and then we do v square average. We if we do v square average, we don't get k Boltzmann d by some.
So it is a generic question that whether the equipartition,
Yes.
because that is related to
Like for the overdamped case, for a simple overdamped case, is it valid?
Because see, equipartition it's kVt, like if you have temperature, then I think the equipartition is there. Right, Obishekta? Is equipartition? It's valid. As long as the
You should think of velocity.
yeah, you should not think of velocity.
Only displacement square.
Only displacement square.
By unit time.
Velocity we assume it's kVt.
It's kVt there. So that means that the equipartition is already there.
So
It's there.
but the equation doesn't show that up. Suppose we write v equal to k Boltzmann.
So this discussion is again this is like going back to this how to from underdamped how to people go to overdamped approximation and all. But underlying velocity is already equilibrated with the existing path. So therefore we are not including the dynamics of the velocity in the equation of motion. So it is always after some time, tiny time, where the velocity variables are equilibrated. That's why we are not thinking about, not writing about any velocity in the equation of motion.
So if you follow the protocol which Edgar said, you change the stiffness, then there will be work, right, possibly, because lambda dot is a data function.
Sorry?
Then if you change the stiffness suddenly, then lambda dot will be non-zero, right?
Yeah.
Is there a what? So
yeah.
So then you will have W naught to be equal to 0.
Yeah. So whenever there is a quench, it means your system, you change the energy to a higher energy level into benefit, and it's considered as work. So
yeah, so here it is, I put the work, I can put the work to be 0 because this protocol, lambda dot is 0, I am not touching the key.
I think this is not a quench, so this is a relaxation.
Relaxation dynamics.
Relaxation dynamics to a equilibrium state.
I say quench because people who do these things like glass or something, they prepare a system in some temperature and suddenly quench it in some other temperature and see that that's, in that language it is.
So the way, in the experiment, the way I would do this is to highly confine a particle and then open a trap and let the particle go. Let it go. Of course, in that initial instant, there is work, but I think you're not counting.
Yeah. So if I change the K, then I don't count the work, but if I change the temperature, then there's nothing to change.
But should it not be consistent with, like, if we have this overdamped thing, if I calculate x as a function of time we have calculated. So this x dot, I mean, this is different x dot. I mean, when you have a thermal velocity like
this is not
this is
that
x.
So this x, if you take the dot and then, so there is no velocity here.
Right. This is not the this velocity will not
Yeah.
be corresponding to that velocity. Which is
There is displacement, but not the. So now, okay. So beta, so I miss it now. So now see, delta S dot. So these are the, so to say, not like they are average numbers, so they are non-random. So alpha, beta, kappa is non-random, but x0 and x they are random. And not only that, this delta S total is a function, is a quadratic function of h0 and x. That means that it will not follow the same distribution as x0 and x. It's a nonlinear function. So, and x follows Gaussian distribution, but E of delta S total will be non-Gaussian. Is it clear? Because my x is Gaussian and it's a quadratic function which is not linear, right? Okay, this S total is the quadratic function of x, so it is not Gaussian. You have to calculate it. Okay. So you can, maybe you can try as a tutorial also that you try to calculate. So how non-Gaussian it is. This you can try to calculate. Obviously you will see that x0 to the power 6 will come, x to the power 6 will come, and they are all non-zero. So it will be a non-zero case. That means your P of delta S total is non-Gaussian. Correct?
So this is moment or Q moments?
This is third moment. You can calculate directly from here. X6 and then you can go to the equation of motion and solution. And so one way you calculate these things.
So under some sense, in this case it is quadratic function because of the term alpha x.
Because they don't. So later I will do where it cancels the quadratic term and then we get a linear function of x. But here this is alpha. This thing doesn't cancel. This sigma square minus t.
Oh, beta x. beta is also having x square or
Square.
X naught square, x square, both are there.
Can we say it follows a chi-square distribution?
I know you have to calculate it. You mean the P of delta S total, right?
It's like chi-square distribution is the sum of z square, not k.
Maybe yes, I haven't tried it. You can try it. You can just calculate. So I will calculate the distribution here. You can calculate the moment also independently.
So how you concluded that the third moment of entropy is not equal to 0?
Can you just say it?
So how you concluded?
Okay, so the point is, this is the function. It is a quadratic function. You can, so this is not a linear function. That is why it is not following the Gaussian. It is non-Gaussian, and typically non-Gaussian has odd moments, non-zero, and you can directly calculate from this the odd moments, and it will come out to be non-zero because all these powers will get to the power 6, which is evening. Okay. So now let's try to calculate. It will be a little bit cumbersome, but let's see how far we can go. So P of so what is my P of delta S total? So this is by definition. I think this morning Abhishek already mentioned this thing, that this is at any time t, this is the initial thing, then I need to have joint distribution of x and x0, and then I have a delta function minus this. So we do repeated times, and each and every those trajectory we collect. So what is the basic thing that why we write this equation? Because we do repeated times the experiment, and each and every trajectory that produces exactly this amount of delta S total, we pick up those, and that this is the distribution, right? This is the definition. Now from the definition you can calculate. So the next, so this is the distribution that we want to calculate, and why we want to calculate? Because we want to validate the fluctuation relation in this particular case, whatever has but so let's try this way. How to? So first we need this P of x, x naught, and at time point. Now we know that x naught is a Gaussian variable. We have chosen it, right? X is also a Gaussian variable because it is a linear function of eta. Eta is Gaussian. So this will be a multivariate Gaussian, right? So how you write that? So this is P of x, x naught t. This is, we first write and then explain. So this is determinant of some matrix A. Minus, this is some vector, I will explain what is it. this, A inverse, then you have A so this is the multivariate Gaussian probability density. This one or what? This one. So this is a joint distribution of x and x naught. Now x is Gaussian. We have explained that this x is a linear function of theta. X naught is chosen to be Gaussian. So their joint distribution will be a Gaussian, it's a multivariate Gaussian. So now how I write a multivariate Gaussian? So this is the way to write the multivariate Gaussian. Now what is A and what is that I have to define. So let me first
but what are those symbols? I cannot read from.
Oh, okay. So this is capital A, and this is small a, and this is determinant. D.
But sorry, Arnab, so if both are Gaussian and has only x squared terms, no linear terms, so then why can't you just write x squared into some coefficient? What is the problem?
No, tell me again.
I mean, both. It's a product distribution. Will it be?
So you are saying that why I can't write this x0, xt, so why not x0?
No, it is not a product distribution in this case? No. Oh, okay.
So it's, at any time it will not. If you go long time,
no, I'm saying you could maybe simply p of x naught, then p of x t given x naught.
Given x naught, yes. That is why I mean here.
No, I'm saying
by step.
You can write p of x naught times p of x t given x naught.
Given base. Oh, base. Right. So this is not equal to because you have this p of x naught and given p of x naught. Yes.
No, I mean
that will be easy to evaluate.
Here itself in the symbol we can use different symbol px comma x naught comma t. Instead of that we use px comma t slash x naught.
That is what we have calculated. So in the multivariate.
What is written there? Exponential or what?
Inside?
No, we are not able to see.
Oh.
Just write it bigger. It's a bilinear form.
Base and writing.
A bar minus.
Let me try my best. See. A minus average. Is it better? Is it better?
Yeah.
So this is the dagger or so. Okay, I will do it explicitly what they are. So A, the vector A is x naught x, and this A, capital A, is a 2x2 matrix, x0 squared average, then x, x0, x0 x average, then x squared. Can you see now?
Yes.
So what are these quantities? They're easy to calculate. So if this is the case, then what is A inverse? A inverse is determinant A x square average minus x0 x, then minus x0 x, then x square. It's not x square. This is not. So if this is A, this is A inverse. That's what we need there in the distribution. Sleepy? What is these quantities? So x, xt was, I just rewrite whatever I have written earlier, x0 into the power minus 80 over gamma. So this we have already done, over minus gamma by gamma integral eta into the power k prime over gamma. And we have already calculated what is x squared average. I just quote here. That was written so long back. So that was there. I am just not rewriting. So x, I just only have to read. This is a new thing. Right? So again, this is simply x0 square into the power minus k, which was sigma. Because x0 is independent of eta, it's a chosen variable, so we can statistically independent, they are 0. So this is the only new quantity, all other thing I had earlier. So I know what is my A, and therefore I know what is my A inverse, and the determinant of course. So I know what is P of x, x naught t, explicitly, correct? Is it clear to?
Sir, how do you write that form of P of x including smaller than
And that's what you mean the whole this one. So the logic was like you have, it is a joint distribution of two Gaussian variables. So it should include all the moments. So all the moments means if you have two variables, there are 4 different kinds of moment. Like x square average here, x naught square, and then x naught average, x naught x average. So that's what it is. And in this particular problem, I can explicitly calculate all the moments for any time. Therefore, I know all the full distribution.
He's probably asking you the algebra of the delta function thing to the next step.
Okay, that I haven't done yet. Yeah. So I just calculate this one so far. Only this part I'm up. So now still I have to manage this. How to manage this? Okay. So there. So let's go on with my P of, so far I have calculated P of x, x naught t. So this we can now calculate full thing, P of delta S total. So t of x naught is there, and I have now the full distribution. So this thing, so whatever inside I know explicitly in terms of x and t, right? They are the moments and everything. Right? So, but what about this? The delta function we can represent as another integral. So, e to the power 2 pi r, some variable r, this is delta function. Correct? So if you rewrite this thing here first there, and then you have, okay, whatever inside that average A, all the moments, this plus 2 pi r alpha by 2
So can you please tell about this representation of delta?
This one? So, okay, Fourier of this. So this is delta of x is right?
So you have used this information, I mean directly you put this form of p x comma x naught t is that will be multivariate Gaussian, right? But in principle you have to start with like, because the probability of x naught you have, probability of x you
So
have.
here we are actually exploiting the simplification, I mean simplicity of the model. That we have chosen a Gaussian initial condition, then the process is also linear because of harmonic trap. So x becomes also Gaussian, and therefore we have a joint distribution which is multivariate Gaussian. So due to our choice, the simplicity appears and we are exploiting this.
And the probability what you have calculated for px, that probability was actually conditional probability because you started from the initial condition x.
So that is why Abhishek was saying that it is better to write px than x naught, like that, right?
Yeah.
So,
missing that. Delta is t is missing.
Delta. Oh, right. Sorry, yes. So this.
Minus I.
E to the power. So there again, 2 pi minus 2 pi I delta S. Yes.
okay, my question is that now it's written, the argument S dot is not appearing anywhere.
Which one? Delta S total?
Delta S total.
It's there. I was just missing. It is there. So Abhishek pointed out.
Okay.
It's there.
Sorry, but in the first line, so I see it in the second line. Maybe.
First line also is there.
First line also I missed.
I see. Okay. This exponential of that times.
Yeah.
Right.
Exactly. Otherwise, it will not have any meaning because all other variables are integrated out. What left is delta S total. So now, why I am doing this? Okay, before, see, what is this function inside exponential? It is a quadratic function because this particular terms, they are all quadratic. Like either it contains x square average or x0 square average, or x square, basically x not average, x square or x0 square or xx naught, right? So generically there is a quadratic function of x. This is also, you have alpha by 2 x naught square, beta by 2 x square. So basically what we are dealing with is this one. If I some coefficient, say a1 x naught square, a2 x square, if I rewrite it properly, then I have some thing. This will contain my delta S total, and a1, a2, they are all functions of R and all. So at the end, so as we have considered only Gaussian, everything is Gaussian here, we are getting the quadratic function that makes the problem doable. Right? Okay. So now, even so this integral can be done because it is a Gaussian integral. But what I am saying is you need not to validate. So the aim is to validate the fluctuation relations, whether it is valid or not. Just test. Of course, it is valid, but we have to test this particular system. Now, this way, if you continue, this integral is doable. You can do it, and then you can get at the end that what is the whole distribution. The algebra is, due to these coefficients are big, so I can show you the result here in the graph, which is better maybe, because otherwise I have to. It's a whole lot of algebra, nothing else.
You can do the R integral.
R integral, we have to do. Yes.
You can do.
Because R is even simpler because there is no R square. R square will not appear.
But when you do the x integrals, there will be some complicated function.
There is some, there may be some, yeah, there is a complicated function of R, but you can manage to.
You will have the form.
Yes, I have the graph of, I don't know whether I can, because it's very, like very large or something. I don't know whether it will.
So R will come 0, right? After the integral of x square, R will come 0, right? In the Gaussian.
R integral will, it's a very complicated function of R. Yes. So by the way, this is from a paper. I will maybe at the end I will.
No, so you can, I mean, whatever function it will come, it will be function of R and.
No, you have to. You have RDR there as well. Not here. So when you represent this one as e to the power this thing, then you have another integral of R.
You have it.
I have it there also here. So at the end, you get a function of delta S total and
yeah. Multiplied with R.
So after all the functions, there is functions of R and a non-trivial integral.
Non-trivial integral of R, and then you can manage to do R also, the integral. Then you finally get the distribution as a P of delta S total in this particular problem. And then you can actually go through the testing, like whether P of delta S total over P of minus delta S total, whether it is to the power delta S total or not. You can do in this particular, but I will from this point of time, I will use a trick. I will not calculate explicitly the full thing. I will use a trick to validate fluctuation relations. Okay. So this, okay. So how it look like? This. So these are the distribution that one can. You just forget about these things. So these are the distribution that you can have after calculating these. So they are non-Gaussian as expected. Okay. And yeah. So this is from this paper. So anyone can.
How is it?
I think they are asking if you can zoom in.
Oh, acha, acha.
In the computer.
This one.
Can the integral over be done? Because rather than there
This is there is a difficult integral, but can be done. You have to go to contours and then find out the poles, and that's why I'm not doing it. It can be done.
This is an analytical theorem.
It's analytic. Yes. But no. This is analytic and then simulation. These are the simulation dots and for various parameters. Right. But it can be like it is there in the appendix of this paper.
So what is T here? I'm just trying to what is the time T here?
Oh, that is so it is also tested in simulation. So what we do is just exactly that I mentioned. You prepare the system in this with the sigma square and all, and then let the system relax. And this, how long it will relax? This is the.
This is all transient.
This is, of course, the whole phenomena I'm talking about is transient.
So even T equals 100 is kind of a transient state of.
Yeah, it is almost towards the equilibrium, but not very close to 100, exponentially close.
That is why it's becoming more and
more.
As we
Exactly.
But during at all these times, fluctuation theorem is still valid.
That I have to check. That I am going to check why it is valid.
Even when it's not Gaussian.
Even when it is not Gaussian. Correct. All the time. And this particular system has a kind of exceptional property that in the morning Abhishek mentioned that there is a steady state fluctuation theorem, right? It is devoid of this transient. You throw out the transient, your system goes to steady state, and then this P of delta S total by P of minus delta S total before delta S total is valid, is there, right? But this particular system, as it is linear, it is valid for all time. Even the transient fluctuation, so-called transient fluctuation theorems, they are valid for even, steady state fluctuation theorems, they are valid for transients as well. Because of the simplicity of the system. Okay. And of course the IFT, the integral fluctuation theorem is anyway valid for all time.
Just to get an idea. So we are leaving a colloidal particle from this position. We are assuming it had a Gaussian distribution. At all times while it is transiently, it's moving to another equilibrium position. It always has a Gaussian distribution.
Yes.
But the entropy production
is not.
Can be non-Gaussian.
Yes, because it is a nonlinear function of x.
Okay. Okay, fine.
But anyway, that is, x distribution is Gaussian and delta S total distribution is non-Gaussian here. Okay?
Not too sure. At higher time, it seems like probability of breaking second law reduces. Is that a correct conclusion?
That so you have a negative part that Abhishek was showing in the morning. That means that your total entropy in some trajectories can be negative, the total entropy change. And those are the trajectories that's quote unquote valid.
My question is, why is it becoming less probable for violating the second law at longer times?
at shorter times it seems like there is more probability of validation.
You mean why at longer time it is going this direction also?
At longer times the overlap less than, not overlap, the area under the curve less than 0 seems to be smaller compared to the area under the curve for shorter time. If you just look at the area,
The mean is moving in the right.
The mean is moving, yes. You mean that this, if I say for example I integrate from 0 to this for this particular curve, say,
that seems to be decreasing.
that seems to be, that will decrease. That is expected, right? Because it is reaching towards equilibrium. Right? So that is why the area under the curve is decreasing.
So on trajectory level also you are saying if you are going to a steady state, starting from any state.
We are going to equilibrium.
Equilibrium, let's say equilibrium. And on an average it will be less likely to violate the second.
Yes, that is what we are saying. Yes.
So at a very long time, the negative part will completely vanish?
No, because it will still be there, and because it is a small system, it is a single particle, and the fluctuation has considerable effect all the time. If you take, say, many interacting colloidal particles, then I would expect that you have a.
So it's basically because it's mesoscopic, meaning just one particle.
One particle and this thing. So fluctuation has more effect in this. So here actually the importance of the stochastic thermodynamics, why we do it. From this curve, this little bit you can motivate this thing that yes, fluctuation do have some considerable effect in this particular system.
Usually it looks like as time progresses, it starts looking more symmetric.
Yes, yes. That is also true. But why? Not very clear to me as well.
I think compared to Gaussian, a long time. Symmetric Gaussian is positive.
Okay. The point is why it is converging to a Gaussian. So you can think of it as forgetting the initial conditions slowly over time, and then the function that S total that I will show in the next example, that becomes a linear more, so it is becoming more Gaussian. So if I start from an equilibrium,
but we still have the excess square equilibrium.
yeah, that is there. But if I start from equilibrium, then your delta S total will be a function of x. And as you go far from the non-equilibrium, non-thermal distribution, it is forgetting, and it's as if it starts from some equilibrium. So your delta x total, the function is like a linear function of x and x. That's what's happening.
Like saying how far from the equilibrium you are using.
That we are up to there. We can actually measure how far it is from equilibrium by introducing some information theoretic measure. That at the end I will tell you. Actually how far we are from. Yes. Okay, let me then. So I will finish by saying mentioning the trick that I am going to use to validate. So it is very general trick. That's why it is not. So this particular trick is not applicable to only this system. So it's an analytical trick, but we can use it for many other cases also. First one is very simple. I need to validate this one. Okay. Now, of course, we can calculate P of S delta total and then explicitly integrate, then show it one. This is one way. Instead, what we can do, sometimes it is easier to do in this way. Take the Fourier transform of this. P of R, say, R is the Fourier conjugate of delta S total. This is what? This is e to the power I R delta S total, P of delta S total correct, if you leave this 1 by root 2 pi constant, etc. So this is, now it's very easy. But if I put R is equal to I, just mathematically it is, means I don't find any physical reason why to put R is equal to I. Just mathematically, if I put this, then immediately it says correct, and this is my right hand side becomes yes. So now the trick is, that's simple. I have this, say, or maybe I don't have explicit form, I just have this delta thing, okay? From there, I can directly take the Fourier transform of e to the power I R delta S, okay, with this all delta is there, so many. Then I put, so this is my P of R, then I put P R is equal to I, setting there, set R is equal to I, and I can calculate the Fourier integral. That is easier in comparison to others, okay? And check whether it is 1 or not. Clear? So this you can do explicitly in this particular problem. Okay, let's do it then. And okay, this is for this, the IFT. And what about this? You can test that if I have. So this actually done, I guess it is in some heat fluctuation, steady state heat fluctuation theorems by Cohen. I forgot the second author, in 1997, 8 or something. Cohen, no, it's not with Gallagher. Benzer. Yes. So what about this? For this, you just test whether it is P of R, whether it is equal to P of I minus R or not. So if it is equal to, then this is valid, this is there. But if it is not, then it is not valid. Typically in the transients, when you include the transient processes, then this particular relation reflects the symmetry that we are talking about, this fluctuation that is required to get the fluctuation relations. Okay, but this is the trick that we follow, and it can be done. So the basic thing, we have to calculate the Fourier thing. Okay. Say again.
Are we not just checking at a single point in Fourier transform space? So how we can say it will valid throughout the space? Just I is a single point, some one point.
That is true, but the point is all the theorems that mentioned, they are defined in the delta S total space. So they can be tested in some single point in the Fourier space. But our aims is to validate, or whether it is validated or not, to check that in the delta S total space. So let it be in the one point in the Fourier space. Okay. So it guarantees it is valid for all delta S total. Okay, so that means that the Fourier calculating the Fourier transform of ds p delta s total is important. So let's calculate it. So let me be a little quick then. So P of RT, which is a Fourier transform of P of delta S total. So this is dx naught P of x naught xt to the power IR So this particular thing we already know. Now if I have this one, then I can just say this. So I can take e to the power IRK here, this is a constant in outside, then dx. So this I can note as a notation. So my x naught x is the vector A. So dA, this I write here, and this I already know, and this is the quadratic function. So all together, I'm just a little bit trying to be quicker here. So that A is there. Other matrix B. So what is this? I will in a moment I will mention. So this is there, and this B matrix is A we already know. B is coming from here. If I rearrange a bit, so B is alpha beta 0 0. So this is my B. So this you can immediately evaluate. So what is this? So this is so e to the power I r kappa 2 pi little a. Then you have that A inverse that unit matrix yes. Okay. So now we can apply easily that A B is det A det B, so that means this will give you 1. So it is okay. So write it here. So P of R T is e to the power I R det minus R. So this is your Fourier transform of the entropy distribution. And then you can directly put R is equal to I. You will see that e to the power minus delta S total average is 1. And then you will also see that if you have this P of I minus R, that transformation, you will see that it is also valid. That's what I'm saying. This is the particularity of this simple system, that the transient, steady state fluctuation theorems also and the integral fluctuation theorem both are valid. So this is here, but one thing I need to tell, because otherwise Edgar will be in trouble later, or he will make me as a anyway, so I have to. So this is it. You can take this example and explicitly calculate in functional forms all the thing. Now what I am up to is just to relate the entropy production in general, not in this particular system, in general, to relate, so this is a small thing, relate to some information theoretic quantity quickly. It's already there, we just want to landscape. So we already know that delta S total forward is minus P of say x naught, P of say x, okay, n. So this is n step and this is x naught. Then I have beta q, and then it is, so in general it is like ln p of x naught, p of, so this is the path thing, so I am writing it very in short notation with an arrow. So this is the whole path probability and this is the initial condition, initial probability. Then I have this final thing, that this is the thing that Abhishek repeatedly mentioned this morning. So this is the general form of the fluctuating entropy. Now, if I have say this, that what about delta S total average? So this is integral P of x naught, P of x naught path probability, then integrated over all path, so that is why this curly D, and then I have dx naught dxn, and then I have delta S total forward. This is a function of everything here. So this I write as, using this definition, the P of x naught, P of x n, then ln of this P of x naught, P of x naught x n, and then I have P of x n, P of x naught from x n, reverse path. So this is my total entropy, but now this is in the information theory thing, it is just as the distance between two probability densities, which is the Kullback-Leibler distance, right? If I write it in, so this is one probability density. Say this is my this capital P 1, and this is 2. This is P1, right? And then I have the Kullback-Leibler divergence with this notation. P1, how it is different or how far it is, quote unquote far, is P1. So all the distributions in the distribution space has this measure or this distance, but it is different. Okay, this is so this is my delta S total average. So this people say is metric, but in a normal sense it's not metric, because if I interchange this P1 and 2, it is not same, which is normally in a geometric space metric is like that. If I change 2 point, then the metric remains same, but it is not like that here. So this is the Kullback-Leibler divergence, which is equal to our average total entropy here. Okay. So this means the forward. So this is the mathematical precise definition of the difference between the distribution along the forward path and the backward path, and this is equal to delta S total average, which is the arrow of time. So that is why we say that how the forward path is differed from backward path is measured by the average total entropy produced. This will be used, I think, by Edgar in the later lectures in some particular context. So there it will be helpful, I guess. Okay, that's what I wanted to. I wanted to comment something, but you know.
I did not understand. Can you just explain that delta S total line that you have taken?
So this delta S total is a definition. This is definition, right? This is fluctuating.
Yeah.
Now I want to average it. Average on what? Average on the initial distribution and the forward path probabilities over that.
So initial distribution and all possible forward.
All possible forward path. So now then I have to multiply both sides with this. This is the initial distribution, P of x naught, P of x naught towards xn, right? So this is path probability, this is initial. I multiply with this two both sides. Then average, then take the integral, which will give you delta S total forward average. And in the right hand side, this is the definition of Leibler-Kullback or Kullback-Leibler divergence. So, okay, let me be a little bit more clear. So I'll come to this point. First I do the math, that will be better. Let's say you have two different probability distribution and you want to quantify how it is different from one to other. Now these are functions, these are not points. So you have to take devise some kind of quantity which will tell you how this function is different from that function. This quantity is Kullback-Leibler. Okay, what is that? Say I have two distribution P and Q. Then log, and I want to calculate how P is different from Q. These two distribution. Then the device is P over Q taking log P integral all. So this is my D P Q. This I devise to right, not geometrically, you can think of a kind of, say, vector space. Okay? This vector is here in the space, this vector is here in the space. How different? For example, in my exam, in the particular problem that I did, you start with some distribution, which is initial distribution. It will land up on some final equilibrium distribution. Now I can ask that how it is different. The initial distribution, how it is different from the final distribution. Then, if I want to ask and I want to get an answer of this, then I have to calculate this, where my P is the final one Q is the initial one, and then take the average and get some number which will give you the distance. Distance in that probability density space. Oh. Then it will show up here in some way. You try to calculate, it will show up. Okay? Then 1, then 0. There is no log.
Log 1 is there.
So that is why they realize that clever people.
Like the delta is totally this one. If I integrate it won't match now.
No, that is why the forward path is different from the reverse path.
Delta is for each path is different.
Then your PR changes. That is why we need this asymmetry is needed here. It is not a simple geometric not in the matrix, not in the distance between you and me. Because if I sit there and if you here, then our distance is small, but this I don't need. We need a difference because of our arrow of time.
What is the motivation?
Okay. So
how is motivation for this measure?
This is actually what this point is. This is, see, if I have same, say, one trivial case, I have same distribution, P and Q are same, then I should have 0. I am getting it, right? And then in this particular